In this video, we're going to talk about the algebra that you can do with complex numbers. So in the introductory video that I made, I've ended it with two things that we're going to explore. So we're going to explore the following. And at the end of that video, I said we'd look at the algebraic operations of plus and times on the real numbers and how those can be extended to the complex numbers. And then the second thing we'll end up looking at later is how the Euclidean distance, measuring how far 2 points in the plane are from each other, how can I do that to measure how far apart two complex numbers are. So this video is to explore more deeply number one. So how does the algebra I know and love from the real numbers, how does that extend to the complex numbers? So let's start with plus. So how do you define addition of two complex numbers? And so if I have two complex numbers, z and w, so z is a plus ib, and w is c plus id, and remember here, a, b, c, and d are just real numbers. I want to talk about what on earth z plus w should be, and so let's define it as a plus c plus b plus di. And what do I want you to notice? I want you to notice that we're just combining like terms. So kind of think about a complex number, think about it as a polynomial, and you can think about I as as a variable if you like. That's how I'm treating this. That's what I mean by like terms. So I just put the real parts together, and then I put the imaginary parts together. And just to say that a little bit more formally, what we noticed just now is that the real part of z plus w is just the sum of the real parts. And similarly, the imaginary part of z plus w is just the sum of the imaginary parts. So let's just do a little example to make sure we're all on the same page with what is going on here. If you want to take 3 plus 4i and add to that 6 minus 2i, we're just going to do 3 plus 6 and then 4 minus 2i. And so you get 9 plus 2i left over. That's all we've got. And let's do one more, say, what if I wanted to take 1 plus 2i, and I'm adding it to itself 3 times, and if I just take the 1's and put them together, and the 2's and put them together, I say I get 3 plus 6i. But now what I want to notice is, you could factor a 3 out of that, so you really do get 3 times 1 plus 2i, and that is consistent with the fact that, oh, I added 1 plus 2i to itself 3 times. And what does that suggest? It's a fact that we're going to use a little bit later on. For any real number, if you have a complex number, for any real number r, and complex number z, r times z should be a complex number as well. And so what that's saying is that you can scale, and what I mean by scale is stretch or shrink complex numbers. Now I want to describe is what are some of the properties of addition that I can expect, and I'm going to try to make a connection to maybe another math class that you've had or that you're going to take, and you're going to see this terminology later on. So I'm going to try to make a connection to abstract or modern algebra, depending on what institution you attend or what your professor likes to call the class. But let me tell you about some properties of addition of complex numbers. And so C with addition satisfies the following things. Maybe how I want to think about this too. You know, I've tried to make a point in the introductory video. So far, just think of C as a set. And now I'm telling you it makes sense to add things in that set. And so here's what you can expect of that operation of addition on your set. So there exists somebody called 0 in the complex numbers, and how it should operate is that 0 plus z should give you back z, and then z plus 0 should give you back z for all complex numbers. And of course 0, the complex number 0, we'll probably just write it as 0 because it's kind of the same thing as the real 0 if you think about it. But maybe more formally think of it as 0 plus 0i. So it's like the origin if you're thinking about it in a picture of the plane. So that's the first thing. So the complex numbers, you should have a way to, you should have some kind of an additive identity is a way to say that. Number 2, for all complex numbers z and w, when you add them together, you should get a complex number back. That's trying to say that the complex numbers should be closed under this operation of addition. I didn't mean to do that. Number 3, for all complex numbers z and w, z plus w should be the same thing as w plus z. That is always going to hold for us. And remember that's called, that says that the operation of addition is commutative. Number 4, scroll down a little bit more. If you have 3 complex numbers, z1, z2, and z3, so those are like little subscripts on those. On the left side here, if you were to add z1 and z2 together first and then add z3, that should be the same thing as if you add z2 and z3 together first, with parentheses, and add z1 later on. That's the right-hand side. And remember, that says that addition is associative. Number 5, for each complex number z, you should be able to find some complex number w that is like associated to z perhaps, such that z plus w gives you 0 and w plus z gives you 0. And of course, what should w be? It should just be negative z. And so z plus negative z gives you 0. What we'll call that is, we'll say that the complex numbers, they have additive inverses. You should always be able to undo your operation. All right, so if I think about a recap of 1 through 5 here, and if you've had like a modern algebra class or abstract algebra, we just talked through the complex numbers with the operation of addition. They form an abelian group. Cool. All right, now let's look at another property. So let's move beyond that. So let's keep going into this, foray into abstract algebra. For any real numbers, R and S, so R and S are just real numbers, maybe think of those as scalars, and any two complex numbers Z and W, the following should be true. So R times Z should be a complex number. That just rescales the complex number Z, and we talked about that above, that we can rescale complex numbers. R times Z should be the same thing as Z times R, so it shouldn't matter what side I put that scalar R on of the complex number. Number 3, R times S times Z should be the same thing as RS times Z. So again, there's some kind of an associativity there. And then here, if I take R and I want to multiply that real number times Z plus W, the sum of those two complex numbers, you can just distribute the R. And so scalar multiplication, it plays nicely with addition. You just distribute in the way that you probably would if you were dealing with polynomials or something. And number 5 here says that you can also do distribution. You can distribute your complex number to a sum of two scalars. So R plus S times Z, you could distribute that Z to both scalars R and S. You get RZ plus SC. And if we are keeping track of what on earth does this say, if I throw this property 6 in with the properties 1 through 5, that actually tells me that the complex numbers form a vector space over the real numbers. And so, again, if you've had linear algebra, that might be where you've run into that terminology before. You might see that, oh, the complex numbers are a two-dimensional real vector space. So this is all kind of going underneath that. That's the definition here that we're tracking through. Let's keep moving. So we're not going to move anymore. We're going to stick here for a little minute. So let's think about, again, we're saying the complex numbers form a vector space. And let's talk about, we had a bijection from R2 to C. We said the plane of points, the Euclidean plane, x comma y, that looks an awful lot like the complex plane x plus iy. And to describe what it means to say it looks an awful lot like it, we're just talking about some kind of a relabeling. I take the point xy, I relabel it as x plus iy. So that's what t does here. It's my relabeling function. We said that's a bijection. But now I've got some like algebraic operations that I can do. So this actually turns out to be an isomorphism of vector spaces, so that this is an isomorphism between the vector space R2 and the complex numbers C. And so let's talk about what does that mean again to be an isomorphism of vector spaces. Good review of some linear algebra here. So remember, what you've got to show is that when I apply t to a sum of two inputs, in my case 2 points, xy and uv, I would put those together inside first. So then again, treating that as a vector, I'm adding two vectors together. And so I just know I add the components, x plus u, y plus v is the second component. And now I think about what does t do? And if you look up at my definition of t just takes the first coordinate, x plus u, and that should be the real part of my complex number. And similarly, the second coordinate, y plus v, ought to be the imaginary part of my complex number. So t should send this point to x plus u plus y plus vi. And now what we're going to do is just kind of pull this apart and put it back together in a neat way. I'm going to get x plus iy together, and I'm going to get u plus iv together, and now I'm going to think, how are those related to t? And if you look at that first group there, x plus iy, that's t of xy. That's the output of xy. And then u plus iv is the complex number associated to the point uv. And what we just showed is that this function t, it's additive, right? T of the sum of two things is the sum of the outputs, is what we just kind of wrote down. And what else do I need to show you? To say that this thing is an isomorphism, we also need to check that it plays nicely with scalar multiplication. So if r is a real number, then what if I was to rescale this point, or this vector x comma y, and I know that I just need to distribute r to x and y. That's what this says here. And now I want to think about what's the complex number that t sends that to. So t sends that to rx plus I ry. And now, what do I know about complex numbers? I know that I could factor that r out front. And I get r times x plus iy. And finally, I see that's r times t of xy. So what that also tells me is that t plays nicely with scalar multiplication. So both of these properties about, t plays nicely with sums and t plays nicely with scalar multiplication, remember that shows that t is a linear map. So I've got a bijection that's a linear map, and again, that's what it means for R2 and C to be isomorphic vector spaces. Now let's keep moving on. So addition, we just covered a lot of ground with what it means to say that you can add complex numbers together, and then the way that you can add them together. We wrote down all the things you could expect from adding complex numbers. Let's talk about multiplication now. So how we're going to define multiplication is as the following. If you took two complex numbers, a plus ib and c plus id, so z and w in that case, we're going to say z times w. For here, just for emphasis, this very first time, I went ahead and wrote the little dot between z and w. From now on, for the rest of my life, I'm never ever going to write the dot. It's always just going to be z next to w. Anyway, what is it? You should do a times c minus bd, that's the real part, plus I times AD plus BC. So AD plus BC is the imaginary part. And if you look closely, all I did was I FOILed. And we'll do a concrete example in a minute. But foiling, remember, that's like a way to distribute. At least that's what we say here in the States. And you're going to remember the rule is that I squared is -1. Now let's do a concrete example just to make sure that it's not too hard or too crazy where this comes from. So I want to multiply 3 plus 2i times 4 minus i, and I'm going to FOIL. So I'm going to take 3 times 4, and I would get 12. I would do 3 times -i, so -3. 2i times 4 is 8i, and I add that, and then minus 2i squared. And now I think about combining like terms, but also, remember I squared is -1. So out there at the end, that's really plus 2. So I get 14 as my real part of this number. So 14 is the real part, and then when I do minus 3i plus 8i, of course you get 5i. All right, so again, I just FOILed, and then remember the rule that I squared is -1. Now let's look at some more abstract modern algebra. Again, it's good to try to tie different classes together so that you start encountering these words more often and they sink in. It's fantastic. So I think I'm on property 7. So property 7, and these are going to be facts about multiplication. So what kind of good things can I expect as far as complex multiplication goes? Is it commutative? Can I distribute? How does it play with addition? Can I distribute is what I mean. Anyway, we'll get there. Number 7. For any two complex numbers, z and w, when you multiply them, you should get a complex number back. So that says that the complex numbers are closed under this multiplication. So it's never going to be possible that you multiply two complex numbers and get something that's no longer a complex number. Number 8 says that complex multiplication is commutative. You can multiply in either order. ZW is the same as WZ. Number 9 says that complex multiplication is associative. And so if you do Z2 times Z3 first and then times Z1 on the left, that's the same thing as Z1 times Z2 first and then times Z3 on the right. Number 10 says that complex multiplication plays nicely with complex addition. In other words, you can distribute. So Z1 times the quantity Z2 plus Z3 is the same thing as Z1 Z2 plus Z1 Z3. Number 11, there exists something called 1 in the complex numbers, such that 1 times z is the same thing as z for all complex numbers. And so we'll call that 1 a multiplicative identity. And again, when you're thinking about this as a complex number, you're probably thinking 1 plus 0i. So you can kind of think of it as, the real 1 is like the real multiplicative identity for the real numbers. And it's the multiplicative identity for the complex numbers too, for all intents and purposes. Number 12, for all complex numbers z and w, if it was ever the case that z times w gave you 0, you know for a fact that z had to be 0 or w had to be 0. Now, you might remember, or you might encounter soon, the terminology for this says that there are no zero divisors in the complex numbers. And if you're interested in zero divisors, think about like modular arithmetic, like z mod 4z. Anyway, we're not going there in complex analysis, but just to try to bring some of that stuff in. So the complex numbers don't have zero divisors. They work just like the real numbers do. Two things multiply to 0, then at least one of the factors had to be 0. And the last one, number 13, if you took any non-zero complex number, so my notation there is c minus the single point 0, so that says all complex numbers besides 0. Anyway, if you take any non-zero complex number, there exists some complex number w such that z times w gives you 1. And what we call w is the multiplicative inverse of the complex number z. So a multiplicative inverse that multiplies to give you back 1. To give you an example, like the multiplicative inverse of 3 would be 1/3 as far as like rational numbers are concerned. And I can say a little bit more. If z is equal to a plus bi, then w, its multiplicative inverse, is going to be a divided by a squared plus b squared minus b divided by a squared plus b squared, and that times I. So you might think about where that comes from. If you've heard of complex conjugates before, I'm going to talk about them in a later video, but there's a good chance you've heard of them before. Yeah, you could think about how to get it from there. All right, so then if I took 1 through 5 together with all of these properties 7 through 13, notice I skipped over 6 though, I don't really care about scalar multiplication. If I take these though, that tells me that the complex numbers with these two operations of addition and multiplication, it forms a field. And so again, a field is something that has these two operations where you should be able to undo them both essentially, and they should work nicely as far as what order you do them in, etc. That in a nutshell is 1 through 5 and 7 through 13. So the complex numbers are a field with these two operations.